those of you who saw the original announcement will realize this. I've inflated the talk. The reason, from 100 years to 150 years, the reason is that the field of topology is just about 150 years old, and what I'm talking about really goes back to the very beginning. So it seemed churlish to neglect the first 50 years. Well, I'm going to talk about spheres, but spheres of many different dimensions. And there's a standard model for the sphere in each dimension. Start easily with a one-dimensional sphere, which is just a circle. Notice by a sphere, I'll always mean the boundary of the sphere. The part inside, in this case, is usually called a disk, or if we have a two-dimensional sphere in 3 space, the inside is called a ball. But I'll be talking about just the surface. So this is one-dimensional because if you want to describe a point on the circle, you just need one angle. Oh, and well, I feel that this is superfluous for most people here, but we can draw a picture of a circle, but if we want to talk about a 17-dimensional sphere, it's hard to draw a picture, so one has to use formulas. In the case of a two-dimensional space with coordinates, say, x and y, and the points with distance 1 from the origin from the circle with the equation I've written there, which goes back to Pythagoras. Now, well, there's a lot, of course, circles have been around for a long time, especially in the form of the wheel, or whose rim is a circle. So this was the oldest picture of a circle I could find. So the circle, whoops. Oh, this is the circle. I don't know why it seems to be a wind-up horse, but I'm sure there's some explanation for that. The biggest example of a circle I could find was these lines in the Peruvian desert, which are as big as several football fields. So anyway, circles have been known for a long time. And two-dimensional spheres have also been known for a long time, but still going back to the circle. So I want to look not only at the standard round circle, but distorted versions of it. For example, this is a famous fractal called the Koch snowflake, which for my purpose is a sphere. It means that one can choose a one-to-one correspondence between points of the standard circle and this, so that as you go once around the circle, you follow a very wiggledy path around this. So this is another kind of thing I want to look at. Here's a smooth circle, a smooth one sphere. Here I've drawn it very thick so you can see it, but you should imagine it as being an infinitely thin line. And this is no longer in the plane. It's now supposed to represent something in 3 space. What does it mean to say that it's smooth? It means that first of all, imagine this is an infinitely thin line. If you just pick any part of it and look at it with a very powerful magnifying glass, then it will look straighter. And if you look at it with a really powerful microscope, it would look just like a straight line. So that's the definition of smoothness, that it becomes straight if it's magnified enough. And the curve is not smooth because no matter how much you magnify it, it will still look very crinkly. That is, if you take this little square here and blow it up, it will, I keep pushing the wrong button. If you just take this little square and blow it up, it will exactly cover this square. So any of the little wiggles you see on this square really should be present in the little one. And then there'll be, if you take a small, very tiny piece, you have to blow it up more, but no matter how much you blow it up, it will always look roughly like this. It will have about this degree of crinkliness, so it never becomes straight. Of course, this this is a definition that only makes sense mathematically. In the physical world, it doesn't make sense to blow up forever because at some point you get down to the atomic scale and so on. So when we're looking at a physical object, you have to first take a mathematical model for it, which is better behaved. Okay, now on to the two-sphere. So this is a standard two-dimensional sphere. It's two-dimensional because it takes two real numbers to describe a point on the Earth or a point on the sphere. For example, latitude and longitude. And again, we can describe it by an equation. This time there are three real coordinates, x, y, and z. And again, you have the same equation, which goes back to Pythagoras. Well, I wanted to find an example of a very old picture of a round ball, but all the old pictures I could find, they didn't have enough sense of perspective so that you could see the roundness. So I had to be satisfied with something like this. Okay, now, again, I want to talk not only about the standard round sphere, but also about rugged objects. So this is a very big rugged object, about a half-mile long. It's photographed by a Japanese space probe. Now, as I said before, when we're talking about a field or a real physical object, we can't magnify indefinitely. So what I really mean by this is that if you can imagine a mathematical object which looks like this from a distance, but which would be rough no matter how much you magnify it. And here's an example of a smooth sphere, so that if you take a magnifying glass and blow up a little bit of it, it will look like a flat plane. This is a very small thing. I should have brought it along. I would have fitted in my pocket. So those are examples of smooth spheres and rough topological spheres. Now, there's I've used the word homeomorphism, saying that Koch snowflake, for example, is homeomorphic to the standard circle. Here's a very important example of homeomorphism called stereographic projection. So if you take a two-dimensional sphere and lay it down on a flat surface, and so with the South Pole touching the surface and the North Pole above, then you get a correspondence between the sphere and the plane as follows. Any point on the sphere, you draw a line joining it to the North Pole, and it hits the plane in a point P prime. And conversely, if you take the point P prime and draw a line to the North Pole, it touches the sphere at one other point P. So this works almost everywhere. The only time it doesn't work is if you try to choose P equal to the North Pole. Let's see what. Well, a similar argument works in any dimension. You can easily check that it works in dimension 1, and if you just write out the formulas, putting an n-dimensional sphere laying it on an n-dimensional plane and carrying out the same construction, you get a similar result. So this defines a smooth homeomorphism between the sphere with a single point removed, namely the North Pole, and the plane of the same dimension, the space of n real variables. So what do I mean by saying this is a smooth homeomorphism? Well, again, you have to think of blowing it up. So suppose you take a very powerful microscope and blow up around this point so that the sphere looks just like a plane, and you don't have to blow this up. The neighborhood is already a plane, but if you use the same microscope, same magnification, then the mapping from up here to down here will be a linear map, a map which carries straight lines to straight lines. And conversely, the map in the opposite direction from up here to here maps straight lines to straight lines. So that is the meaning of what I mean by the word smooth homeomorphism or diffeomorphism. Well, the three-dimensional sphere is, I can't really draw a picture of it, but we can write down the same equation. Now, we take the space of 4 real variables and look at the set of points of distance 1 from the origin. The three-dimensional sphere has played an important role in cosmology, one possible model for what our universe might look like. So this is a kind of sketch of, well, of course I can't draw a three-dimensional sphere. This is a sketch of a two-dimensional sphere, but you're supposed to imagine it's, whoops, keep pushing the wrong button. You're supposed to imagine that this is covered with many, many galaxies. This is exaggerated, of course. The galaxies are too big and there aren't enough of them, but you imagine there are galaxies scattered all over it, and now as the sphere expands, the galaxies fly away from each other. And as far as I know, this is still a viable model. I don't think it's the most popular one, but I don't think it's really been disproved. Well, the first historical description I know of a three-dimensional sphere occurs in the Divine Comedy, which is not where one would expect to find such a thing, but Dante was concerned, of course, with heaven and hell. He knew that the earth is a round ball and that hell was supposed to be down, so the only logical place to put it would be in the center of the earth. Here's a picture of Dante wandering down towards the center of the earth to inspect. But where does heaven go? Heaven was supposed to be up, but up from where? Was it above Italy or above England? Or it seemed unfair to put it above any one place, so his solution was that no matter where you are, if you go up, you should come to heaven. So he defined a universe with concentric spheres around the earth, which first get larger and larger as you go up, as you would expect, but then they start getting smaller and smaller again until finally they squeeze down and enclose heaven. Well, now let me get back to the mathematical problem. How can you recognize whether some given, say, subset of Euclidean space is topologically a sphere? Well, the two-dimensional case was solved 150 years ago, which is why I changed the title. So if you look at closed two-dimensional surfaces, there's just a simple list of them, closed orientable. There's the round ball, the round two-dimensional sphere, a donut-shaped surface of a donut, surface of a pretzel, and so on, a pretzel with many holes. Möbius described this list and said it was everything, although it wasn't really proved till much later. But in particular, we have the simple characterization of the two-dimensional sphere. If we have a closed surface, that means a surface without any boundary, which is enclosed in a finite region of space, then if it has the property that any closed loop on the surface can be continuously shrunk to a point, then it's a sphere. So you see on the sphere, if you have a little wiggly loop, a little closed curve, you can just shrink it down without ever leaving the surface. But if you're on a torus, if you have a curve that goes around like this, there's no way you can shrink it down to a point without leaving the surface. And similarly in the higher genus case, if you have a little circle that goes around like this and you try to shrink it to a point, there's no way you can do it without leaving the given surface. Well, Poincaré asked a very famous question in 1904. He asked whether the same thing works in dimension 3. So suppose you have a closed three-dimensional manifold with this same property that any closed loop shrinks to a point. is it true then that it has to be homeomorphic to the three-dimensional sphere? And this seemed like a natural question, but it took 100 years to find the answer. Well, for the first 55 years, there were many, many attempts to answer this question, many different ideas, reducing it to a problem which sounded simpler, but somehow the simpler problem always seemed too hard also. I promised I would give some examples of things that didn't work, which, well, let me just give one. This is a picture of Henry Whitehead. I have very fond memories of visiting Whitehead in Oxford, where his wife had a hobby of raising pigs. So this is an honest picture. He claimed a much stronger result, that if we have a closed manifold that has the property that any loop can be shrunk to a point, then if you remove a point from it, it will still have this property. So you have if you have an open three-dimensional manifold, one which is allowed to go on forever, if you like, and if every subset can be shrunk to a point, then he claimed a proof that it was homeomorphic to the Euclidean space. But then he took a closer look the next year and found a counterexample to his own theorem, which is, I guess, humiliating, but it's better. It feels better if you find the problem yourself than having somebody else point it out. So he just constructed a very complicated, complicated subset of the sphere, such that if you removed it, you find a counterexample. Well, there was another important result during this period, which was not a deep theorem. It's almost a trivial remark, but it plays a very central role. This is a theorem of Georges Rabe, who considered a manifold and a smooth function from the manifold to the line. So again, smooth means that if you magnify a little point here and magnify the corresponding point of the line the same amount, then it becomes a linear function, which takes, well, which takes lines to well, I guess taking lines to lines on the straight line doesn't quite work, but I think you know what a linear map is. So his theorem is that if there is a smooth function with only two critical points. Now, a critical point is a point, if you think of the height function as in this picture, then a critical point is a point where the tangent plane is horizontal. So in other words, if you keep magnifying this, it will turn into a horizontal plane. And if you keep magnifying around this point, the surface will become a horizontal plane. But if you magnify around any other point, then you find that you get a plane which is not quite horizontal. And the proof of this was really very easy, because you have the gradient lines, which are indicated by arrows there. At any point on the surface, you can look at the direction. If you think of you're sitting on the surface and you want to walk straight uphill, then the direction you would follow is given by that arrow. And so if we just start with a little neighborhood of the bottom, which is take a little two-dimensional disk around this point, and then just slide it up along these gradient lines, you can slide it up so that it will cover the whole sphere and prove that everything with the top removed is a copy of the Euclidean plane topologically, and therefore the whole thing is a copy of the two-dimensional sphere. And the same argument works in any dimension. Okay, now it turns out that Poincaré's question becomes much easier in higher dimensions. This was amazing to everyone, but nobody expected it, but it turned out to be true. But I have to change the statement a little bit before it makes sense. So let me state the generalized Poincare hypothesis. If we have any closed n-dimensional manifold, and if it has the property that any proper subset, any subset which isn't the whole space, can be shrunk to a point within the manifold. If that's true, then the manifold is homeomorphic to the sphere of the same dimension. And, well, this is not an easy statement. The proof took a lot of work by many people over many years, but it provided a kind of guide to understanding many kinds of things in topology. So all of the work that was spent in proving it was not just spent in studying this isolated example, but understanding the structures of all kinds of manifolds, things which are often important in many applications of mathematics, not only in pure mathematics, but also in many applications. And the big surprise, as I say, is that the three-dimensional case turned out to be the very worst. So Poincare had started out by posing the hardest problem of this nature. Well, so the first breakthrough in dimensions 5 and above was made by Steve Smale. He announced it in 1960 and filled in the details in 1961. So he proved this generalized Poincare hypothesis for manifolds of dimension 5 or above, but he had to start out by assuming it was a smooth manifold. So he didn't claim anything for rough manifolds, things like the Koch snowflake. He assumed the manifold was smooth and then constructed a topological homeomorphism. And his proof just depended on Rabe's theorem. Given any manifold, you can find smooth real-valued functions on it, but in general, they have lots of critical points. So what he did was devised a procedure for canceling one critical point against another, so that just assuming that every loop can be shrunk to a point, he got rid of the critical points 2 by 2 until there were only 2 left, and then he could apply Rabe's theorem. Well, this started the ball rolling. At almost the same time, John Stallings and Chris Seaman used a completely different method, and instead of assuming that they were working with a smooth manifold, they assumed they were working with a piecewise linear manifold, one which could be cut up into linear pieces. So this is an example of a piecewise linear two-sphere. But they got the same result. Starting with the piecewise linear two-sphere, they got a topological homeomorphism. And then a few years later, Max Newman and Ed Cannell showed that you could modify the Stallings argument so that you don't need to have a piecewise linear structure. Just a topological manifold would work. Proof of the topological generalized Poincare hypothesis for all manifolds of dimension 5 or more. And since the 1- and 2-dimensional cases were already known, that left only the 3- and 4-dimensional cases to still open. But that's saying a lot, because 3 and 4 are precisely the cases where none of the arguments seem to work. Well, Michael Friedman was the one who finally solved the 4-dimensional case. So in 1982, he proved that the Poincare hypothesis is true in dimension 4. And unlike the other arguments, he didn't work with smooth or piecewise linear objects at all. His proof was purely topological and used very wild topological arguments, very complicated. In fact, his arguments are strong enough to classify all closed-oriented, simply connected four manifolds. Simply connected is what the description of the property that every loop can be shrunk to a point. Well, I can't describe the proof, but even though this is a paper about four-dimensional objects, it's full of illustrations, and I just copied a especially charming one. This is his picture of a kinky handle, which plays an important role in his proof. I should mention that Friedman has changed fields since then. He's now the director of the division of Microsoft, which is trying to build a quantum computer. So he's very much concerned with practical problems now. Well, that covers dimension 4, and we're left with dimension 3. Now, in the same year, 1982, Bill Thurston made a very important contribution. His geometrization conjecture covers not only the three-dimensional sphere, but any possible closed three-manifold. So his conjecture stated that such a manifold can always be cut up into a finite number of pieces, cutting along spheres and toruses, so that each piece has a very simple structure described by a kind of classical geometry. And in fact, there were 8 kinds of classical geometry that had to be considered. The one we're concerned with is spherical, so looks like a round sphere. But there's also the Euclidean geometry, which is flat. There's the hyperbolic geometry, negative curvature, like saddle-shaped surfaces. And there are 5 other geometries that I won't try to describe since they're more technical. But the spherical case is the only one that concerns us now. Well, he was able to prove this conjecture in some special case, some quite general special cases, but he didn't have anything to say about the spherical case. But if this conjecture is true, then the Poincare conjecture would follow as an immediate corollary. It's a kind of structure theorem for arbitrary three-manifolds, and it's sharp enough so that if you know the manifold is simply connected, if it has this property that loops can be shrunk to a point, then it would follow. Well, the first real attempt to prove the geometrization conjecture, which would include the spherical case, was by Richard Hamilton. He introduced the Ricci flow method. Now, this is something like a heat flow. If you know that if you have an uneven distribution of heat over some solid or some body, then it will heat will flow from hot to cold, so that in the limit, everything has the same temperature. And he was trying to construct a differential equation which would have the same property for the geometry of a manifold. So if you have a manifold which is highly curved in some places and not in others, then the curvature would flow from the highly curved part. And the hope was that in the limit, you'd have a kind of uniform distribution of curvature all over the manifold. So for example, in dimension 1, if we start with something like this, where the curvature is concentrated in the corners, and apply this Ricci flow, then the curvature would gradually spread out so that the corners become less curved and the curvature spreads out more and more. And in the limit, in this case, it would work. You end up with a perfectly round circle. And in fact, he was able to carry out this argument in special cases. So in some cases, he could prove that this would really work and converge towards a round sphere. But the problem was that in the general case, take an arbitrary curved manifold, which has this property that every loop can be shrunk to a point. It just didn't converge. It converged. What happened was it tended towards singularities, which are very hard to understand. Well, just 10 years ago, Grisha Perelman managed to get around all of these difficulties. He used extremely delicate arguments, often motivated by mathematical physics, to prove the full geometrization conjecture, proving that he could take any one of these singularities and figure out how to smooth it out and make it go away. So this completed the proof of the generalized Poincare hypothesis in all possible dimensions. I should mention that Perelman is a very interesting character. He spent a year in Stony Brook many years ago, and he was a legend afterwards. I wasn't there at the time, but the stories are marvelous. Apparently, he wanted to visit the South Shore, but didn't like cars, so he walked to the South Shore. And he was famous for having very long fingernails. And apparently he lived very frugally while he was in Stony Brook, so he saved all his money and could live for 10 years afterwards in Russia on what he'd saved. And of course, it's well known now that he scorned the prizes that he was offered. He felt that this was an insult to just, he produces this beautiful mathematics and people insult him by offering money in return. And I think he was so disgusted, as last I heard, he had given up mathematics and was spending his time studying the Torah. Okay, well that finishes the description of the generalized Poincare hypothesis, but now I want to look at a variant form of it. So in Poincare's time, one didn't especially distinguish between topological manifolds, smooth manifolds, piecewise linear manifolds. It was sort of generally assumed then and for the next 50 years that these were all more or less equivalent. You picked out whichever definition was what most convenient for whatever you were trying to do and assumed that it didn't make any difference which way you started. So we could just as well have phrased his question a little differently if we emphasize smoothness instead of topology. So we can ask about the smooth generalized Poincare hypothesis. So this would be the following statement. Suppose that a smooth n-dimensional manifold satisfies the conditions of the generalized Poincare hypothesis. In other words, it's a closed manifold, and every loop, every proper subset can be shrunk to a point. Does it follow that it's smoothly homeomorphic to the standard sphere? Well, one way we could try was try to solve this is by applying a famous theorem called the Weierstrass approximation theorem. So applying it in this case, it says the following. Suppose we have a homeomorphism from M to the sphere. So M is a smooth manifold, and we have a homeomorphism giving a one-to-one correspondence with points of the sphere, which is a smooth mapping. I'm sorry, no, just a homeomorphism, a topological homeomorphism. Can we approximate it by a smooth homeomorphism? Well, his theorem says that we can always given any epsilon, we can find an epsilon approximation which is smooth. But the problem with this is that the approximation isn't necessarily one-to-one. So, for example, if you have this some sort of wiggly figure, and you have a homeomorphism to the circle, when you approximate it, you find that you have little wiggles. So as you go back and forth, it may go back and forth here. You don't have a one-to-one mapping, but several points here may correspond to one point down there. But it might seem that if you can do it one way, you can make it work in both directions. But in fact, it's just impossible. The statement isn't true. What happened? Well, the answer is this is impossible. Well, let me describe the history of this. So, about 55 years ago, I was trying to understand some examples of eight-dimensional manifolds. And I got into a quandary because I seemed to be able to prove something which couldn't possibly be true. Well, dimension 8 is a little hard to visualize, so let me start by describing a easier example. So here we have a Möbius band, so that means it's a one-sided surface. If it's I should have brought along a strip of paper which is bent into a closed loop with a twist, so that if we start on the front side, for example, and go around it, and follow it around, and then we suddenly find ourselves on the back side by the time we come around. And such a Möbius band can be mapped down to the standard circle in such a way that over each point of the circle, you find a whole line segment of points of the Möbius band. So similarly, down here, take a point down here, we'd get a little line segment like that. Here, a little line segment like that. And so this line segment I want to think of as a one-dimensional disk. In general, the n-dimensional disk is well, if we think of the n-dimensional sphere as being described by taking n real variables and setting the sum equal to 1, then we get the disk just by putting this by including things where the sum is less than or equal to 1. So in particular, in one variable, we just have the equation x squared less than or equal to 1, or in other words, x is between minus 1 and 1. Now, one important point to notice is that the boundary of a Möbius band is a circle. If you start here and go around, you come around, and if you go around twice, you get back to where you started. So the boundary is also a circle. Well, that's to kind of illustrate the kind of thing I want to talk about, but I need it in higher dimensions. So unfortunately, I can't draw a picture of higher dimensional manifold, so I've just used the same picture. But now you're supposed to imagine that this, down here we have an n-dimensional sphere, and up here we have a 2n-dimensional manifold, and we have a mapping down, and with the property that over each point here we have not an interval but an n-dimensional disk. Here I've been, maybe I should be a little more clear here. I've been talking about three different categories of manifolds. Closed manifold, things like the sphere, the surface of a donut, and so on. I also need to talk about manifolds with boundary. So the standard example would be a disk, given by this equation, where the boundary is a sphere. And the third class of manifolds I'm talking about are open manifolds, So examples would be the Euclidean space or the sphere with a point removed. So here, this E2n is a manifold with boundary. And if we take the preimage of any point here, we get a little disk, which is itself a manifold with boundary. And the amazing thing about such examples is you can often choose such things so the inverse image of a point is a copy of a disk again. Oh, now, well, that's no longer amazing. I guess you could do that easily. The amazing thing is that you can do it so that the boundary is a sphere. So the first example of this is called the Hopf fibration. It was discovered by the Swiss mathematician Heinz Hopf. He described how you could take a three-dimensional sphere and map it down to a two-dimensional sphere so that the preimage of any point is a circle. So you have circles twisted around each other in the three-dimensional sphere, but not intersecting, and so that the quotient space is a two-dimensional sphere. Well, there are higher dimensional examples of the same thing, and I was particularly concerned with the case n equals 4. So I found many examples with n equals 4. So here we'd have a 4-dimensional sphere down here, a 8-dimensional manifold with boundary, and the boundary was a topological 7-dimensional sphere. And the proof that it was a topological 7-dimensional sphere was just the same argument due to Georges Rabe. So one had construct this explicit smooth real-valued function with only two critical points on it. Well, this seemed fine, but then I tried going farther understanding this. My goal was to look at closed 8-dimensional manifolds. So what I had was a manifold with boundary. Here, this n is now supposed to be 8. So we have an 8-dimensional manifold bounded by a 7-dimensional manifold, and we compare it with the 8-dimensional disk, which is bounded by a 7-dimensional sphere. And I had examples where, using Rabe's theorem, we could prove that this boundary was a topological sphere. So it was natural then just to glue this sphere onto this sphere and get a closed manifold. But now suppose we know that this homeomorphism between this sphere and this one is actually a diffeomorphism. Then we could use the same construction, and it's not hard to round off the corners and get a smooth manifold. So in that case, we could take this manifold we get by taking the 8-dimensional manifold with boundary, pasting on an 8-dimensional disk, and getting a smooth 8-dimensional manifold. Well, this looked perfect, but there was a problem, because there were a lot of known restrictions on what the possible topology a closed smooth manifold would have. This followed from the work of René Thom in France and Fritz Hirzebruch in Germany, who'd studied the topology of closed manifolds and by very ingenious arguments found all sorts of relations which had to be satisfied. And the problem was that a number of these manifolds which I thought I'd constructed couldn't possibly exist. So I was left in a quandary for a while, but the only way I could figure it out was by assuming that this map between the topological 7-sphere and the honest 7-sphere could not possibly be made smooth. I'd proved they were homeomorphic using Rabe's argument, but there had to be some obstruction, something stopping it from being a smooth homeomorphism. So what this showed was that the smooth generalized Poincare hypothesis is just false in dimension 7. Well, this led to many natural questions. What's special about 7? What happens in other dimensions? So I was, well, let me first describe a way of adding two manifolds together. So suppose we have two closed manifolds of some arbitrary dimension, smooth manifolds. Then if you cut a little round hole in each one and paste the two together, you get a new manifold which is connected. So this operation is called the connected sum. And this turned out to be well defined. That is, it didn't matter where you chose this little disk. It would still come out to be the same up to diffeomorphism. It is important they have to be oriented. Did I say that? Yeah, oriented manifolds. If you paste a right-handed manifold onto, if you get the orientation wrong, then you wouldn't get a unique sum. But if you assume that manifolds are oriented, that means if you, say in a 3-manifold, this means if you have a right-handed glove in the manifold and you carry it around a loop, it will never come back to be a left-handed glove. Well, this operation is commutative because it doesn't matter the order of the two manifolds. It's associative. That means if you have a row of 3 manifolds, three different manifolds, it doesn't matter whether you first paste these two together and then paste these two together, or whether you do it in the other order. So you describe this by saying that the set of all oriented diffeomorphism classes forms a commutative associative semigroup. You know how to add them. You know the addition is commutative and associative. And it also has an identity element. If you take any manifold here, like this donut, and add a sphere, well, if you cut out a little disk in a sphere, then the complement is another disk, and when you paste it back in, you get a copy of the original manifold. So this gives a kind of structure for the set of all manifolds of given dimension. Now the natural question is, can a manifold have an inverse? If you're given a manifold M, can you find another manifold N so that the sum is a sphere? And Barry Mazur gave a very easy answer to this. The manifold has an inverse if and only if it becomes Euclidean space if we remove a point. And we know that that implies that M is topologically a sphere. And the proof is kind of magic. You just use this same connected sum operation, but paste infinitely many things together. So first, suppose, for example, that we take an infinite sequence of n-dimensional spheres and paste them pairwise together. Then I claim that we get Euclidean space. So here's a picture if we take one-dimensional spheres. So here I've taken a row of one-dimensional circles and pasted these two together, pasted these two together, and so on. And now if you take this and just think of grabbing the ends and pulling it out, you'll pull it out to a straight line. And similarly, if you take this figure and just rotate it around the horizontal axis, you'll get a similar picture with two-dimensional spheres pasted together. And again, you can just think of this pulling out operation, moving things, pulling things up here and pulling things down here, and rotate the whole thing about the axis. You get you show that the corresponding thing corresponds to a two-dimensional plane. And similar things work in any dimension. So now suppose we start with Mazur's condition. You have two manifolds such that the connected sum is a sphere. We'll just take an alternating sum, m plus n plus m plus n. And if we put in parentheses, since it's associative, m plus n is a sphere, m plus n again is a sphere. So we have an infinite sum of copies of Sn, which we've just shown as Rn. But on the other hand, we could put in parentheses a different way. Suppose we put it m, and then n plus m, then n plus m. And then, since we know that this is a sphere, and so on, we're just taking m and adding the sum of spheres, which is Rn to it. Well, what is m plus Rn? You can think of Rn as being a sphere with a point removed. So if you take Mn plus Rn, it's the same as taking Mn plus Sn and then removing a point. But remember, Sn is the identity element, so this is isomorphic to Mn minus a point. So putting this all together, we see that Rn is diffeomorphic to M with a point removed. Well, I've shown that the first thing implies the second. I won't try to prove that the second implies the first, but it's a fairly routine argument. And I've discussed already the fact that second implies the third. So this proves his lemma. I mean, it's an amazing field. Things like this theorem or Rabe's theorem are almost trivial to prove, and other things which look more complicated require years of hard work. Well, I worked with Michel Kerver on studying such questions. So, well, I described the connected sum for arbitrary manifolds. Now I want to concentrate on manifolds which are homeomorphic to spheres. So we're looking at smooth manifolds which are homeomorphic to spheres. And we already know that in dimension 7, there's an example which is not diffeomorphic. So we can look for the corresponding problem in any dimension. Well, it's clear in dimension 1 that we get a trivial group here. Add a circle to itself. We get a circle, and there's nothing much else. It follows from Möbius's result that we don't get anything interesting in dimension 2. It follows from Perelman that we don't get anything else in dimension 3, although, of course, that wasn't known when we did this work, but we now know that there's nothing interesting in dimension 3. We studied the case where n is at least 5, and we proved that this is a finite abelian group. The word abelian is in honor of Neil Hendrik Abel. So abelian is just a synonym for commutative. But in talking about groups, since Abel was the first person to study this kind of group, they're called abelian groups. So in the next two cases, dimension 5 and dimension 6, again, we found there was nothing interesting happening. In other words, the smooth generalized Poincaré hypothesis was true. And in dimension 7, as I pointed out before, that we get something non-trivial. In fact, there are 28 different differentiable structures. Dimension 8, there are 2. In dimension 9, there are 8 with this complicated group structure. In dimension 10, there are 6. In dimension 11, there turned out to be 992. In dimension 12, the smooth generalized Poincare hypothesis again is true, and so on. We couldn't go much beyond this. Our methods involved reducing the problem to standard problems in algebraic topology, which were known up to about this level. Nowadays, people have gone further and can compute these groups up to about dimension 62, but still, there are severe problems in algebraic topology which keep us from going much farther today. Okay, well, so I've described what happens in dimensions 5 and above, what happens in dimensions 3 and below. What about dimension 4? Well, there, no one knows. Simon Donaldson first brought powerful tools of gauge theory to bear on this problem, and he showed that many of the simply connected manifolds that Friedman described couldn't be realized as smooth manifolds. And the combination of these two completely different methods, Donaldson's methods from gauge theory and Friedman's methods from complicated topological constructions, just led to amazing results when you put them together. So, for example, Robert Friedman and John Morgan shows that a closed topological manifold can have infinitely many essentially distinct differentiable structures. These are local people. Friedman is at Columbia, and Morgan is the director of the Simon Center at Stony Brook. Cliff Taubes at Harvard proved that if you just look at the topological space, four-dimensional Euclidean space, it has uncountably many distinct differentiable structures. So there are uncountably many manifolds which are homeomorphic to R4, but not diffeomorphic, and no two of them are diffeomorphic to each other. And this can only happen in dimension 4. Neither of these phenomena can occur in any other dimension. So what does one know for the set of differentiable structures on the 4 sphere? Well, they form it's a commutative associative semigroup with unit. That just follows more or less trivially from what I said. And it's not hard to show that it has most countably many elements. But what isn't known? Well, everything else. We don't know whether this is trivial, whether the smooth generalized Poincare hypothesis is true in dimension 4. We don't know if there are only finitely many structures, whether it's a finitely generated object, whether there are inverses. All of this is unknown. Okay, and let's see, here is just a couple of references of expanding on what I've talked about now, in case you're interested in more detail. And are there any questions?
We're explaining the first group.
Yeah.
What makes 5 dimensions and also special compared to 4, 3, and 4?
Well, the basic thing is that there's more room to move things around. It turns out that things like the circles and two-dimensional spheres in the spaces play a very special role. Most of the complications come from then. And if you have 1 or 2-dimensional things in a high dimension, you can just push them apart and not worry about them. Whereas if you're in low dimensions, then things get in the way and you can't move them around without running into trouble. Yeah?
Earlier you talked about proofs that involve the flow of curvature.
Yes.
Is there curvature in general relativity is associated with gravity? Very interesting, if possible, physical interpretation. Could be some dynamics in that flow of curvature?
Well, so the question is whether the flow of curvature, what kind of curvature, how is it related to general relativity? The question is, the answer is that it's very closely related, because Einstein's gravitational equations essentially involve the Ricci curvature, which is a kind of average curvature which has especially nice properties. And it's precisely this Ricci curvature which Hamilton worked with. So it's just setting up a differential equation where you have a manifold with a metric tensor which has a certain Ricci curvature, and then you change have a flow in the metric. So the metric changes depending on the Ricci curvature, and you get a differential equation which superficially looks very much like the heat equation, describing the way heat flows. Now, if you're asking whether this has direct connections with general relativity, I don't see any, but certainly they're defined in the same mathematical framework.
We live, perhaps, in a four-dimensional manifold. So what are the implications of having many different structures of the space that we live in?
I would guess that there are none, because I put it this way, I would think that the fact that one has gotten a much greater understanding of three-dimensional manifolds might be important for cosmology, because there is a real possibility that the universe in the large has some non-trivial topology, and if there is a non-trivial topology, it would force strong restrictions on what we might be able to observe. So I think that has direct relations with physics. But I don't think the exotic differentiable structures, as far as I know, would lead to anything observable or anything that would impinge on the physical world.
I have a question about the mathematicians rather than the mathematics.
Okay.
Is there any professor-student relationship among all these mathematicians, or they just read each other's papers and fall away?
I can't think of any direct student-professor relationships, but it's a relatively small world. I think these people mostly knew each other or know each other, or if not in person, by reputation, and ideas flow quickly.
One more question. Yeah.
Perhaps an esoteric question. As an example, you've mentioned the snowflake,
Yes?
which in principle cannot be even a one-dimensional object, right? Because the boundary is fractal. However, the topological properties sort of can be classified.
Yes, well, there are different meanings for the word dimension. I was talking about topological dimension, and topologically it's one-dimensional. But of course, if you want to look at so-called fractal dimension, it's certainly a dimension larger than one. I mean, you can have a, if you like, a fractal topological circle which has positive area. There's nothing to prevent this. So it certainly would have fractal dimension too. So I was talking only about dimension in the topological sense, the number of real variables needed to describe a point. Mm-hmm.
Just one more. Okay.
You mentioned pure mathematics, but I'm curious. I assume that computers and computer graphics play a big role in helping people to visualize functions. And there is this one famous person who claims to visualize a three-sphere. Has he ever convinced anybody else that he really knows?
Who is this person? Well, I think Bill Thurston certainly was someone who had amazing visual abilities, could visualize higher dimensions very well. He unfortunately died a few months ago. There are many different kinds of mathematicians. Some stick very closely to their epsilons and deltas and writing down very precise proofs, which in theory a computer could check, and others have visualization and see things that the rest of us can't see, and somehow miraculously always, Thurston was certainly a case where he could see things and he was always right, even though, he could also write down proofs, but he was more famous for just inspiring other people.